Welcome to the AERA Solutions channel. In today's video, we shall be looking at an example on the resultant of two-dimensional forces. That is, forces that are acting on the plane. And we're going to be working through a series of problems. And we're going to start with this first sample, in which we're given that the tension in cable BC is 725 newtons. And we are to determine the resultant of the three forces exacted at point B of beam AB and its moment about C. So look at the diagram critically, and you see beam AB, and we're to look for the resultant forces, that all these three forces, the tension, the force of 780 and the force of 500 newtons, are exacting at the point B, and we're going to find the moment of that resultant force about point C. To solve this problem, the first thing to do usually is to produce what you call a free body diagram. And the free body diagram is just a section that shows all the forces acting at a point with other bodies removed from it. So for this case, this is our free body diagram. And let's not forget, having produced the free body diagram, we are to look for the resultant force Fr. And we know that basically resultant force is the sum of all forces added up together. And to add up these forces, we need to take them to their component forms, that's in forms of X, Y, and Z. But for this case, because it's a force acting on the 2D plane, that's on the because it's a two-dimensional force system, we're going to have components in just the X and the Y axis. And to find these components, we just apply a simple formula where we have that the force is equal to the value of the force times cos theta to give the X components, and that same force times sin theta to give the Y components. I'm going to do this for the three forces to find their component form before we add them up. But let's remember that for this problem, we're not given the angles directly for these forces. We're going to start by looking for the component of the force F1 that is equal to 718 newtons, which is at an angle theta 1. And to find the angle theta 1, we need to reproduce this diagram as shown. And this is just a part of the space diagram that we've taken out of it. Going back to what we had, we know that having this, we can easily find the angle theta. We know that sine theta is equal to opposite over hypotenuse. For this case, we have the opposite to be 5, which is the value of the side that is facing the angle. While the hypotenuse is usually the longest side, or the side that is facing the right angle of the triangle. So for this case, our sine theta is equal to 5 over 13. Likewise, our cos theta is equal to adjacent over hypotenuse. Here we have that our adjacent is 12, which is the side that is touching the angle itself. Then we have our hypotenuse to be 13, that's the longest side, or the side that is facing the right angle triangle. So from this equation, we can easily find the angle by saying theta 1 is equal to arc cos of the adjacent over hypotenuse, and in this case is the arc cos of 12 over 13. So we have that theta is equal to 22.61 if you evaluate the theta equal to arc cos 12 over 13. Or you can use theta 1 is equal to arc sine 5 over 13. You're likely going to get the same answer, which is 22.61. So basically, for this force, the first force, we were given that it's equal to 780 newtons. And we've gotten our value for sine theta, our value for cos theta, and our value for theta to be 22.61. So having this value, the next thing we want to do is to find the force in its component form. And we know that the force F1 is equal to F1 cos theta 1 I plus F1 sine theta 1j. Put this into our equation, we have our F1 to be 780 newtons, and we have our theta 1 to be 22.61. And if we evaluate this, basically we're going to have our F1 to be 720I minus 300J. Let's note that the reason, so we're going to have 780 cos 22.61I minus 780 sine 22.61. Let's note the reason for the minus sign. It's because This particular force, if you resolve it, it's because if we resolve this particular force to the vertical axis, you see that it's pointing downwards. So as you can see, the arrow is pointing downwards in the y-axis, or it's possibly for the x-axis because it's pointing rightwards. That's the direction of the x-axis. So it is important I will take into recognition the sense of a force when we are doing our resolution. So if we evaluate this, we're going to get 720I minus 300J. So basically, we are done with the first force. Now we're going to work with the second force, F2, which is equal to 500 Newton, and we're using the angle theta 2. So we start by bringing out the diagram itself. And having gotten this diagram, it's easy to find our angle theta 2. We know that sine theta 2 is the opposite divided by the hypotenuse. For this case, it's 4, which is the side facing the angle, divided by 5, which is the hypotenuse. That's the longest side, or the side facing the right angle triangle. Then also we have our cos theta to be adjacent of our hypotenuse. For this case, it's 3 over 5, which is the side touching the angle divided by the longest side, which is 5. So basically, we can find our theta 2 by finding the arc cos of 3 over 5, and we get our value for theta 2 to be 53.11 degrees. So summarily, having gotten that, we have our force to be 500 newtons, and our sine of angle is 4 over 5, while our cos of angle is 3 over 5. Then also we had our theta 2 to be 53.11. So basically, we can find the components of our force F2 by applying our formula, and if we introduce our values into it, we have our value for F2 to be minus 500 cos 53.11 and minus 500 sine 53.11J. Let's note the reason for the negative sign in this case is because if you resolve this force F1 to the horizontal axis, is going to be pointing leftwards, which is the direction that is opposite the direction of the x-axis. And if you do same for the y-axis, if you resolve to the vertical axis, it's going to be pointing downwards. That's why we have negative values for both cases, both the x component and the y component. And if we evaluate this further, we have our force F2 in its component form to be equal to minus 300I minus 400J. So basically, the last part of this problem is the one that requires the tension. So we're going to walk through to take the tension and force to its components. We're told primarily that our tensile force is 725 newtons. We're given specific dimension, which is the length of the string 1160 millimeters. We had the length of the bar AB to be 840 millimeters and the height of the bar to be 800 millimeters. So with this, we can easily find the angle theta AB. That's the angle that the string is making with the horizontal axis. So basically, we are working with this force, which is 725 newtons. To estimate the angle it's making with the x-axis, we just need to remember our equation. Sin theta AB is opposite of our hypotenuse. For this case, it's 800 over 1160. Then we can also find our cos theta to be 840 over 1160 by dividing the adjacent over hypotenuse. Knowing this, we can easily find our theta AB, that's the angle that is making with the horizontal, by finding the arc cos of 840 and 116 divided by 1160, and that will give us 43.58 as our angle that this string AB is making with the horizontal. So basically, we've gotten our sine theta AB, we've gotten our cos theta AB, we've gotten our angle theta AB. And if we simplify this further and apply these values to our force or the tension between the string, which was given at 725 newtons, we're going to have one straight equation. For this case, it is minus 725 cos 43.58I, because we know that if we resolve the tension, the tensile force to the x-axis, horizontal axis is going to be pointing leftwards, which is opposite to the direction of the x-axis itself. While for the y-axis, if we resolve this force FAB to the vertical axis, is going to be pointing upwards, hence it is positive. And if we evaluate this, basically we're going to have our FAB to be equal to minus 525I plus 500G. So basically we've gotten our F1, which was due to the 780 Newton force. We've gotten our F2, which was due to the 500 Newton force. And we've gotten our tensile force resolved into components as well. Let's remember that we're looking for the resultant of these forces, and we know that resultant is just to sum up all these forces together. That's FR is equal to F1 plus F2 plus F3. So to do this, we're going to add up all the I components together, and after doing that, we add up all the J components together, and that will give us one straight equation, which is showing that all the I components added together and tagged I, as well as all the J components added together and tagged J. So if we evaluate this further, we get that our resultant force to be minus 105I minus 200J. Well, basically, this is what we are looking for. But we also need to calculate the magnitude of this force as well as its direction. So to do that, we have our FR to be minus 105I minus 200J. And we know that our resultant force is the square of both components. If it's three-dimensional forces, you're going to also have Fk raised to power 2. So if you add all this together and find the square root, you likely get your resultant force to be 225.89 newtons. So you can approximate it to mean 226 newtons. Then also we need the angle that this resultant force is making with the horizontal. And this angle, we can get it by finding the arctan using this basic equation, arctan Fy over Fs. So if you find this, basically you get our angle to be 62.28 degrees. But having gotten the angle, how do we reproduce this on the diagram? Let's remember we have our x and y components. Our force FR is equal to minus 105I and minus 200J. So we have our force minus 105I, which means it's pointing in the x direction, then minus 200J downwards. So basically our force is going to come as to where it's meeting these two values. And as a result of that, we have our resultant to be 225.89 newtons. And that is the value that is as a result of the minus 105I minus 200J. Let's not forget that we also have our angle, which we've estimated to be 62.28 degrees, that is making with the horizontal x-axis. So that's that about the resultant. The next part of the question, so that's that about the resultant. So we have our resultant and the angle is making with the horizontal, and for this problem is equivalent to this. So these two systems can be used interchangeably. One singular force of 225.89 newtons at an angle of 62.28 will create the same effects as the tension in the string and the two forces that are attached to the beam AB. But we're not done with the question yet. We're also required to look for the moment about point C. That's the moment of the resultant about point C. And to find moment is usually straightforward. What we have our resultants, we have our space diagram as well, and we have the dimension of the x-axis. So basically, we can produce that same dimension in the diagram, and we're looking for moments of this force about point C. So, and we know that moment m is equal to r cross f. What is r? R simply is the displacement vector. That's the displacement from point C to point B, which is the point of application of the force. If we can find our displacement vector, we can find the cross product with this force, which is Fr. That's the force in its component form. So basically, what's our displacement vector, which can be represented as Rxi plus Ryj. How do we get this value? What is Rx and what is Ry? So basically, Rx is the distance it has traveled in the x-axis by the time it got to the point B from point C. And in this case, it's 840 millimeters. While Ry is the distance it travels from point C to point B in the horizontal direction. And this case is minus 800 millimeters. Let's note that it is minus because, as we can see, to move from point C to point B, we're moving downwards, which is against the direction of the y-axis. Why the RS is positive? Because you discover that we're moving in the direction of the x-axis. If we are moving from point C to point B. So basically, that's why one is minus and the other one is plus. So invariably, we have our arrow, that's our displacement vector, to be 840I minus 800J in millimeters. And that can be written in meters to be 0.84I and minus 0.8J in meters. Then next is the force. We need to produce this force in its component form. Although we've done that before, we know that the force in its component form is the value of the force multiplied by cos of angle I, in addition to the value of the force multiplied by sine of angle J. But in this case, we have negative, negative because they are both pointing downwards and leftwards, respectively, in the y and x axis. As you can observe, if you resolve the resultant to the vertical axis, that force will be pointing downwards. If we resolved it to the horizontal axis, the force will be pointing leftwards. So basically, that is why we have negative values for our x and y component, and our resultant force is minus 105I minus 200G. So we recall that our moment formula requires us to find R and to find F. So these we've obtained. The next thing, how do we find moments, which is the cross product of R and F? And to find the moment of these forces is to find the determinant of the matrix shown. And this matrix contains the displacement vectors and the force. And to do that, we have to replace all the values of Rx, Ry, and Rz by those ones we have inside the matrix. Mind you, for this case, we have Rz to be equal to 0 because it's a two-dimensional system. And you do same for the force. You use the S component, the Y component, and the Z component to replace what you have inside the matrix. And also in this case, because the two-dimensional system, our Fz is also 0. And if you do that, we have this matrix. Next is, how do you find the determinant of this matrix? To find the determinant or to evaluate this matrix is to bring what you call a cofactor. On top of I, put +1, J is -1, K is +1. So then you begin to select what you call a minor. Some groups are used to find determinant of that group. In this case, by the time you pick I as the pivot, you have to strike through all you have there and you strike downwards. And what will be left is this section of the matrix. Then use the top part to multiply the bottom, and you subtract what you have by multiplying the bottom left by the top right. And if you do that, what you have is minus 0.0. What you have is minus 0.8 times 0 minus, then you put into brackets minus 200 times 0. And that's what we're going to have, all multiplied by plus I. Then you do same for J. You select the J component and you strike through. Then what will be left are 4 elements, and you do same, you multiply the top by the bottom right and the bottom left by the top right. So if you do that, you get minus 0.84 times 0 minus 105 times 0. So in this case, you multiply it by minus 1J. So if you do that, you have minus J into the other terms, and you do lastly for K. So you select your pivot, you strike through, then work with the part that remains. By multiplying the necessary parts, 0.84 times minus 200, use it to subtract minus 105 times 0.8. So you add that up to the matrix as well. And at the end of the day, this is what you need to evaluate and simplify to get your eventual matrix. Mind you, and there's also another way. What about displacement vectors? You have your force in its component form. There's also a simple formula that you can apply directly that is derived in some materials. So if you know this formula, you can also apply it directly to find your moments by imputing all the unknowns, all the values you have into this formula, and you evaluate it to get your moments. It's the same thing you will get as if you have done it by finding determinant of the matrix we are illustrating earlier. So this is a faster approach to finding the moments of. This is a faster approach that you can use to find the moment of a force about a point. So if you do that, you get your value for moments to be 0I minus 0J minus 252K. And to find the magnitude of the moment, you apply the simple formula that is used to find magnitude, and you get our moment to be 252 Newton meters. So that's that about moment. So for this problem, we've answered all the questions that were given. We calculated the force, the resultant force, the angle it's making, and we calculated moments. So we're going to see another variety of the same question. In this case, we are told that the two forces and tension in the cable exert a resultant of 105 Newton leftwards and 200 Newton downwards to the horizontal and vertical axis respectively. We are to determine the tension in the cable BC and the length of the cable. In this case, we are given the resultant force, the component of resultant force, and we are required to look for the tension in the cable. So it's a simple thing to do. You just produce your free body diagram, which is the first thing to do. And for this case, you're given a resultant of the three forces. And we have to look for the tension in the cable and the length of the cable. That's what is not given in this case. But it's a similar question to the other one, but this one has been twisted in another form. So to solve this problem, we start by taking the forces to components, starting with the 780 Newton force. We know the procedure. We've calculated the angles before. So you just look for the component form of that force, which is 720I minus 300J. The minus sign in the y-axis is because if you resolve this force to the vertical axis, it's going to be facing downwards, so it's negative. While the positive for the x-axis, if you resolve it, is going to be facing the direction of the x-axis, which is rightwards, and it's going to be positive. So invariably, you do same for the second force, 500 Newton. You resolve the component. What you have, like we've evaluated before, is equal to minus 300I minus 400J. For this case, it is so because, as we are aware, if you resolve to the x-axis, it's going to be facing the direction that is opposite to the direction of the x-axis. So it's going to be negative. If you resolve downwards, it's going to be negative as well because it's facing downwards, which is against the vertical axis. And finally, we're given resultant FR. We're told that the resultant is 105 Newtons leftward, so it's negative, and 200 Newton downwards, so it's negative. Leftward means it's away from the x-axis, which is rightward. So for this case, we have three different forces, but what we are looking for is tension FAB. And we know that to find FAB, we were given this formula before. This is the general formula. Resultant of forces is the sum of all the forces acting on it. For this case, we are looking for FAB. So to look for FAB, we just make subject of the formula, which is to subtract other forces from the resultant force. And we've already gotten values for F1, F2, and FR. So basically, one can easily find FAB by using our FR components to subtract F2 and then subtract F1. And that will give us our I components. So you do same for the Z components. You use a value of FR to subtract both the F1 and F2 Y components, and you get the Y component of FAB. And if you evaluate this, you're going to get FAB to be equal to minus 525I plus 500J. So if you've gotten this, you want to find the resultant of these forces. What you have basically is F to be equal to the square of both sides of both components. So you can just apply this formula to find the resultant of FAB. And if you do that, you get your FAB to be 725 Newtons, as we've gotten earlier. But mind you, we're also looking for something else. We are looking for the length of the cable. To find the length of the string, we know that we need to know the angle. And once you get the angle, you can find that. But we've gotten the component of FAB. And you know that if you have the F component, you can find an angle by finding the arctan of Fy over Fx. This is a general formula that is used to find the angle that the force makes with the horizontal. So we can use this simple formula and apply it to our force FAB in it, which is expressed in its component form to get our angle theta AB, which will be 43.59. Well, we're not actually looking for our angle. Really, we're actually looking for the length. And we know that cos AB is equal to adjacent over hypotenuse. Knowing that cos AB is equal to adjacent over hypotenuse, we can therefore apply this formula by knowing that the adjacent length AB is equivalent to 840. So if we apply this formula directly, we can easily get our length to be 116 millimeters, which is also equal to 1.16 meters. So invariably, we'll answer this question. No matter how it's twisted, you can always find what you're looking for. We've gotten the tension AB on the string AB and the length of the string. So this is also answered and settled. So we're going to quickly look at the third angle of this question. In this case, we're given the tension in the cable BC to be 725. And the resultant of the three forces to be 226 newtons at an angle of 62 degrees. That's the resultant of the play forces. We're also giving resultant of the play forces to the horizontal bar AB. And we're told to determine the values of F and theta and the moment of the force F about C. This is also very simple. How is it simple? We can just walk this through the same steps that we just used to solve sample 2 by finding all the forces in their component form and subtract them from the resultant to get our force F that we are looking for. Then once it's in component, we can find the angle. Then we can easily find the moment of the force F about C. So let's note that for this case, this is what we have. We have our force F1 already given, we have our tension already given, and we have our resultant given as 2 to 6 newtons. So we're looking for F2 and theta 2. So basically you just walk through the same procedure, you find the free body diagram and all that and solve through it, and you're going to get something like this. There are some materials that applies a table of this form to solve problems that borders on force resolutions and moments. So in this case, I've tried to introduce that. So basically, the goal is just to fill this table. You want to you're giving some values, you want to calculate for some others. So in this case, we're giving all these things: the opposite, the adjacent, and the hypotenuse for force 1. We're also given the dimensions of the tension AB, that's FAB, as 840, 800, and 1160, and also the force of the tension itself to be 725 newtons. So basically, mind you, we're also given the resultant. They said it is 2 to 6 and at an angle of 62.5 with the horizontal. And basically, with this formula for cos theta, you can find the angle theta for angles that has not been given to you. So with this formula, you can find the theta for F1, for F2, and for FAB. Sorry, excluding F2 because we're not giving F2. We're actually looking for F2 in this problem. So having found those values of theta based on what is given to you and that simple formula, you can find our Fs components. So with this formula, you can find the Fs component for the resultant force, and you can find the Fs component for the F1 and also FAB. And note the negative and positive signs in the places where they are necessary. Places for negative signs are places where the force, when you resolve to that component, is pointing a direction that is opposite the direction of the axis itself. So having gotten that, you can also find your Fy components by multiplying by sine theta. So if you do that, you can find your Fy component for F1, and you can find your Fy component for FAB and FR. So having gotten all this, it's not very easy to find your force F2, which is what we are looking for in this case. You just write down your formula. Is equal to the resultant minus F1 and FAB. So once you can get this, you can easily find our Fs component for F2, that's the F that we're looking for, and our Fy component for the force we are looking for. And once this is done, you can easily use these two formulas to get your angle and your resultants. And that would have solved this problem. So after that, the next thing is to calculate your moment, which is easy and straightforward. It's just to apply your formula, and once you know what you have and what you're looking for, you apply it to the formula and you can easily get your moment to be 576 Newton meters. I want to believe this is straightforward. So if you can follow through this video, you can solve any problem no matter how it is twisted. Just understand the basic step. The first step is to first identify the angles. Having done that, the next is to take the forces to their components, then you add up to find resultants. But cases where resultant is given to you and you need to find other forces, what you do is you subtract all the forces that has been given to you from the resultant, you get the value of the unknown force. And once you've done that, you are good to go. Then if it's a case of moment, you just apply the formula directly, and if you apply the formula directly, you work it through, you get your answer. So this is straightforward problem, and this year we're going to call it an end for this particular video. So I wish you all the best and I hope to see you in subsequent videos. Thank you.